All right, thank you. Good afternoon. As Chris said, my name's Daniel Austin. I'm Senior Principal Architect for Yahoo's Exceptional Performance Group. I want to warn you, I'm not going to stand up here and edit any JavaScript in VI. And there's no hovers or anything like that. What I want to do is talk to you about what we're doing to use JavaScript and JSON to make the web faster. And if there's any theme to this talk, it's making the web faster by making it smarter. So that's where we're headed. For our agenda today, we're going to talk about a new protocol called Scratch. It's not related to the MIT product that we saw earlier at all. That was sort of an anti-serendipitous moment for me, even though I did go to the Institute. Protocol design is our next agenda item. We'll talk about results and current state, and where do we go from here? Fairly standard agenda. Few words about my group at Yahoo and what we do. A lot of what we do is building tools. I think everyone here knows about YSlow. Anybody not know about YSlow? I didn't think so. Okay, everybody knows YSlow is written in JavaScript. A lot of what we do is optimizing the user experience. Every time you go to a Yahoo page, we're out there trying to make it faster every day. And to touch on today's topic, we do a lot of research, forward thinking, advanced technology. What are we going to do to make the web faster and smarter today? And that's where we're headed today. So our goals, I want to explain the design for the Scratch protocol, why we went where we went, why we are excited about JSON, why we think that it's something that we wanted to come and talk to you about, because one of our goals is to leverage the collective intelligence of this group on making Scratch better. We want to describe our experiments, request some feedback, ideas, improvements, criticism, constructive criticism. Very welcome. So, the first question I always get when I give this talk, right after why am I going to burn the internet down and start over, is why did I call it Scratch? And we started out to design this protocol, performance first in mind, and it went through several iterations. Initially, we ended up rewriting something that looked a lot like TCP. I think everybody that goes through this exercise ends up doing something very similar. We had congestion control. We didn't quite reinvent slow start. I won't plead guilty to something that bad. But we went through this process of redesigning TCP, and that really was not the right solution. And so we tore it up, we started all over again. And we didn't like that version either. We had a bunch of homegrown UDP libraries. That didn't really work for us, so we burned it down again and started over, and we tore it up and we started all over again, and we did that several times. That's why we call it Scratch, because we started from scratch several different times. So, just the elevator pitch. You're in an elevator with an executive. You've got 30 seconds to describe it. I can't do it in 30 seconds, I'm sorry. But maybe 90 seconds. Scratch is a new dual-band data protocol for the web. It's designed to work together with HTTP over TCP, the one we all know. We'll call that the control channel, alpha channel, not related to your 8-bit intensity map. We'll also talk about Scratch UDP, which is the data channel for our protocol. We'll call that the delta channel. If you look at my well-designed engineering diagram produced over here, you can kind of see that we have a erstwhile user going to a set of machines somewhere, presumably a data center, obtaining some control information, and then going out and making requests against what are apparently some data nodes using the Scratch UDP data protocol in order to access that data. This is one of the primary architectures and the intention for our architecture. It looks a little weird until you think about, oh wait, those are CDN nodes. So the way we load pages today, we go and we download the base HTML. We parse through that, gather up all the links, do some other things. And then we go out to the CDN and we gather multiple data objects. Obviously, your small, non-commercial website doesn't do something like this, but all of the major sites do this. Scratch was designed to make that scenario a lot easier. This is not the only scenario. It's just one of them. All of our large commercial providers really want to use CDNs. It helps performance. We're trying to make that work in a completely different way. So this is basically the elevator pitch for Scratch. There's absolutely no detail here beyond this small engineering diagram. We're going to get into that. So, motivation. Why do we want to do this? First thing is we look at it, the web and what we do on it today, and we know that TCP is not terribly efficient for what we're trying to do. Small objects are not terribly efficient via TCP. You can kind of see here we have some graphs showing number of objects and their sizes, Yahoo, Amazon. You can see that these distributions are heavily weighted toward very small objects. This is not a mystery. Most things on the web are not very large. Another issue we have is that parallelism across the browsers is not useful. We all know that the browser tries to gather all the data from the CDN in some parallel way, make it as fast as possible. If anybody's seen a waterfall diagram, we know how this works, but we know it isn't very uniform. I think IE9 opens, what's the browser connection constant for IE9? I think it's 6 connections per unique host name. And in Firefox 4, it's 15 individual connections onto a unique host name. That's a little crazy. And it doesn't work. Firefox is not twice as fast as IE. One of the other problems we have with TCP, there's no context. The server doesn't remember you. Every time you make a request, you have to tell it, yes, I take text HTML. Oh, and I take GIFs too. A lot of redundancy in that information. We'll talk about state and why we need to manage that and the fact that we do manage state today, even though we pretend we don't or we often claim we don't. TCP tries to trade reliability for performance. In a lot of cases, that's a really good trade-off. It's not necessarily the trade-off we want to make on the web. If we're going to make the web faster, we've got to make it smarter. Forcing everything to make a trade-off between reliability and performance in favor of reliability is not a performance optimization. Not designed for small incremental changes. Bandwidth efficiencies are typically very small. So a typical beta for a website, less than 25%. I went and measured the Yahoo homepage. Bandwidth efficiency for the Yahoo homepage, 11%. Never been able to get it past 11%. That's terrible. We've got to be able to do better than that. One of the motivations for Scratch, TCP does not work for the way we want to use the web today or in the future. So some of our goals around this, and obviously work in progress, right? We want to increase that bandwidth efficiency. Could we get 50%? I bet I could. I bet if I eliminated the redundant headers, I bet if I managed the connection state a little more intelligently, I bet if I used JavaScript to send objects down to the browser without a lot of intervening hassle, hey, maybe I could get 50% improvement. What do you think? Once again, the theme of the talk, faster equals smarter. We need semantic awareness. We need managed contexts for the web. Identity, state, first-class objects in the system. We do this today. We manage state. We have persistent connections. It's that HTTP 1.1 thing. We manage state. There's those cookies. Oh, don't get me started on cookies. Just do not get me started. First-class objects in the system for state, identity, for encryption, for several other aspects of things that are bolted on after the fact, should be first-class objects in the web, should not be treated as second-class citizens. Scratch tries to remedy some of those problems. We wanted it to be robust. We don't need all of TCP. And I don't need 30 years of development on TCP. We want to target slow networks, global networks. Not everybody's network works as well as Comcast. We want mobile and tablet devices, low bandwidth Internet of Things chatter. We'll talk a little bit about the Internet of Things and the role JavaScript can play there. Those are really the goals that we set for ourselves. I want to talk a little bit about the design decisions that we made. So when we went to look at all the work that's been done in this space, we found a lot of it. We are not the first people to think of this idea. All of these people are fellow travelers in the goal of making the web faster and smarter in different directions. Some of them are protocols or different layers of the stack. Others are data exchange formats. Others have various aspects. Speedy is something from Google trying to multiplex HTML streams. RackNets, often used by mobile games, multiplayer games. W3C just released EXI. This is sort of a compact binary version of the XML info set. Sort of takes away a lot of the ideas that we had for using JSON to begin with. They're too late to the game for this, but it's on here. Another thing that did not make the slide is something called telehash. I don't know if anybody's heard of this, but I just found it last week. It didn't make my slide, but I suggest that you go and check it out because I just think telehash is doing something extremely cool. Regardless of what you think, all of these folks are heading in the same direction. We tried to first rob these guys of every single good idea they had to their names. And we say thank you to everybody who worked on those because we unashamedly stole your ideas. And we also, I don't want to give anybody the idea that the relationships shown here are really intended to illustrate the exact relationships between Scratch and all of these others. I just want to give you an idea of the multitude of the different groups working in this space and the different approaches that they're taking. As far as I know, we are the only group that's taking the approach based on semantic awareness. All the other folks are doing what we call faster trash, which just means we're trying to shove the same headers, the same web garbage down on the user, make it faster. We call this faster trash. We don't think it's satisfactory. Why UDP? I had one person, I think, said they didn't know what UDP is. UDP is another protocol, not similar to TCP, but has its own things about it that make it worthwhile. It's widely used for all kinds of different things. If you've logged into your VPN lately, you were using UDP for that. Why did we choose it? Need for speed. For various reasons, UDP is just simply faster. This is not something that's unknown. We need flexible multi-point architectures. The little stick figure diagram I showed you earlier with its 3-point architecture is very difficult in your connection-based TCP system. Doesn't make a lot of sense because the individual connections have no awareness of each other. Small messages, transient data. We didn't need consistent ordering. I mean, seriously, does it really matter whether that beacon gets on your page before the ad? Wouldn't you rather have the ad first? You don't care. Neither did we. We tried a different strategy. Instead of trying to do what TCP does and make sure that every packet arrives in time, in order, we just said, hey, you didn't hack us, fine, we're just going to resend it. It's cheap to resend. Resend, don't transmit. There's already a significant amount of prior art, and we wanted it to be very, very simple, which is not something you can say about TCP. So, enough on that. How did we get there? Like I said, originally we started out and we wrote our own UDP libraries. Man, this was really, really a bad idea because we learned a lot about network programming, but what we really learned is that other people had been there before us, and they had already done so much work and put in so much effort that we were never going to catch up no matter what we did, and that we were going to have to embrace and extend and use other people's stuff because on our time schedules with our group, we were simply not going to reinvent everything all by ourselves. We ended up using something called the UDT library, originally developed at Urbana-Champaign, won several Supercomputer Challenge Awards for high-performance data transport. It does a lot of cool things, connection semantics. There's hooks in there to rebuild TCP if you're really dying to do that. We avoided that like the plague. Third generation code works really well. The API is similar to the traditional BSD sockets. Anybody who's done that sort of programming is not going to feel terribly uncomfortable. One problem we had with it is that it's almost too powerful, too many features. We had to strip a lot of stuff out. There was data serialization already built into it. There was a number of things that we did not need. We just stripped all that stuff out. And this pattern of finding something that worked to do what we wanted on the net, stripping everything out, and then using the result is pretty typical for Scratch, and you'll see that as we go through here. JSON. Is Doug Crockford here? I guess not. So I can probably get away with this slide. I was kind of hoping he was going to be downstairs when I put the slide on. Scratch uses JSON as its data layer format. Why? Well, Jeremy Johnson got up here yesterday and he said, you know, well, the reason we do this is because it's JavaScript and JavaScript is cool. I think that's pretty fair description, actually. It's easy to encode and decode, available for all our platforms. The gentleman before me, Tom Fuchs, was just talking about iOS and how it deals with the various JSON aspects. Very important, JSON is true to our ethical standard for the web that everything should be understandable by a human being and that you don't require a machine to interpret anything for you on the web. This is a serious ideal. It's compact and lightweight. We love JSON. How did we live all those years without it? I'm not entirely sure, but now that it's here, we're not going to miss the chance. It just makes everything else a whole lot easier. I don't think this is an audience that I need to belabor the fine points of JSON about. Other audiences are like, what's JSON? Tell us about it. You guys are already sold. I'm standing up here preaching to the choir, and I'm actually enjoying it. So we went to do JSON, and we went and did exactly what we had done before. We stole somebody else's library, stripped out the good parts, and left the rest. In this case, we used an Apache project called Avro. I'm not sure if anybody's heard of it. It was designed to do RPC data transport for nodes on the grid. Doug Cutting, if anybody recognizes that name from the Hadoop world, was one of the primary committers for Avro. That in itself probably means it's pretty good code, but it has some really interesting features. Well-managed current code base for an Apache project. I think everybody knows that's pretty important. A lot of abandoned Apache projects out there. Avro makes JSON a lot more robust by extending the type system, enforcing the types with a well-defined grammar, has self-contained schemas as metadata, and that's one of the cooler features. I'm going to save that feature to the end to explain it in a little more detail because we have something that almost resembles an actual bit of code over here. Oh my God. Another thing that Avro has is it's got hooks in for encryption, SASL, lexical sorting. Oh my God, we can sort things on the web in JSON. This is absolutely required. There's nothing you can do without sorting. Has to be there. One of the best features was really the ability to do the lexical sorting. Against the Avro framework, well, there's not a whole lot of cons. It does exactly what it's intended to do. You know, it was very RPC-centric. It's not bad, but it's not what we wanted. We stripped a lot of that stuff out. We did not use it to compile code. We did not use IDL to define our data types, although we might at some point. What we really wanted was very robust JSON that could be generated at scale. And that was really the key feature, and the Avro framework provided that for us. Just to hit on the point about the self-contained schemas as metadata. This is a key idea in Avro and really a very key idea for programming, I think. In order to consume JSON produced in this way, you don't need anything on the client. You don't need fancy tools, interpreters, anything like this, because appended to the header of your JSON datagram, so to speak, you have added the schema for the data that you're sending. It can be read on-site. It's self-contained, encapsulated with its own metadata. And you can see this ridiculously bad little code segment over here where I'm starting to model a cookie, and you can see that I've got name and value. Like I said, don't get me started on cookies, but I wanted to kind of give you a sense of how this works to attach the schema for the data at the beginning of each datagram, because I think that that is an extremely cool feature. It relieves us of having to do a lot of client work where we would have to build some sort of interpreter. There'd have to be some exchange of metadata. You have to understand what it is you're trying to read, JSON or otherwise. And we found that this approach worked really well for us. You know, I don't know if anybody from this team is here, but if so, we thank you. We're looking out for your stuff. That's basically the part that I wanted to talk about with respect to the protocol design. Just a quick time check and make sure I know where I am. And I don't because my clock stopped, but that's okay. Let's talk about the results. Let's talk about the current state. Just going back through the protocol stack here really quickly for review. UDP on the transport layer, we're using this UDP library for session management, does some encapsulation, connection semantics, stuff like that, not as important as the stuff above it, and that's generally true of any network stack. In true OSI form, I'm using the OSI terminology wrongly. JSON is not a presentation framework, right? Nobody looks at it. Right? It is actually a data exchange format, but it fits nicely here into the OSI stack, labeling it that way with the caveat that we know it's not really a presentation format, but data exchange, still, it fits into the stack nicely, and if we just sort of warp the OSI terminology a little bit, we can probably get away with it. I think everybody knows what I'm trying to get at. Scratch Delta is at the application level. That's where we want to talk about. That's what's really important about what's happening here. So, special plea from the developer of Scratch. I know that all the Node developers are in this room. or at least maybe not. Some of them might be downstairs. But guys, I need your help on this because there's nothing that's more suited for using Node than Scratch. Right? Scratch is about sending JavaScript objects encoded in JSON. What do I need for that other than Node? No-brainer. This was made for Node. Node was invented for this. You guys didn't know that when you invented Node, but now you know. Why can't we use the existing Node situation? Well, UDP support is still somewhat basic. I know that Paul Kerna had written a little UDP transport module for Node. He presented that at Node Camp, and it's very minimalist. There's a PCAP library. Isaac Schluter pointed this out to me. I was actually able to use his little Node package manager, worked really well, and install the PCAP library in Node. It works. I was able to see packets coming across. It doesn't work very well. I need your help, Node guys. Really, I do. We expect that this situation is temporary. Hint, hint. Okay, so enough for the special pleading from the developer here. Let's talk about some test results. So this isn't all blowing smoke, right? We've actually gone and written some code and made things work. So let me tell you about our test setup. We wrote a little app. I'm sure that you can guess we called it Scratchpad. There's a lot of Scratch puns. I'm not going to apologize for them. First pass results. Let me explain to you our test setup. We set up instances on AWS in 5 global locations. Everybody knows, there's one in the East and the West in the US and Europe, a couple in Asia. We set up a circular buffer test. We created link objects, encapsulate a hypertext link. The part of HTML that actually is really interesting and important are the links. So we created 1,000 of those as JSON Scratch Delta objects, and we padded them out to the same segment size as we use for TCP because we wanted to do a comparison TCP to UDP and see exactly what was going to happen. So we padded things appropriately. And you can kind of see some of the results here. I don't know if my pointer's actually visible, but in the table here you can kind of see that if we went to update a single link globally, so remember we've got 1,000 of these, they're out there in a buffer, and we want to update a single one globally, all across the world. How long is that going to take us? 338 milliseconds if we use Scratch, 2,240 milliseconds if we use HTTP over UDP. That's huge. When we went to update all the links, all 1,000 of them globally, imagine how this is going to work. First you have to sort them, first you have to find them, then you've got to modify the link to the new value. We went through, that took us 1,200 milliseconds. And actually, that's right, we couldn't get the HTTP TCP data on this one because it timed out every single time. The next test that we did, and the other thing I wanted to mention here is that we were really concerned about packet loss. I don't know if any of the Google guys are here, but one of the things that they've found out with their Speedy protocol is it's very subject to packet loss, very sensitive to packet loss. We're obviously sensitive to packet loss too. We were really concerned. We did not see major differences in packet loss. Now these numbers, by the way, are only for the Scratch demo. We did not get packet loss numbers for the HTTP transport. So the 0.11 number there is really only for the Scratch data. But you can see the packet loss data is very low compared to what we had expected to see. So that's, it's an interesting test. We did a circular buffer and we updated some objects in memory. It's interesting, and the results are okay. More interesting, still not real, still not in front of a real user, but more interesting is that we tested a real text buffer. We took the Yahoo homepage and we sent it around into our circular buffer, and we looked at how fast we could send that around, and we looked at how fast we could do it if we compressed it. And we haven't talked about compression, but we will. Compression is a first-class object in Scratch. Everything is compressed, except the things that are already compressed. So for sending the base file, Metro, Yahoo homepage, by gosh, 217 seconds to get that puppy around the world. Now, speed of light times around the world are not that much less than that, right? Same order of magnitude. The HTTP TCP method, 3 times as long. I'm not sure, I don't think anybody's really going to be surprised about that. Sorry, I got to stay in the light here. I don't think anybody's really surprised that it takes 3 times as long with HTTP to do this. It is, after all, stateful, or stateless. And we know that because of the size of this object, it's going to be several packets in length, 35Ks, multiple packets. You can see in the graph here, and this is just visually showing what's in the table here, but in the graph you can kind of see what the result is. 3x for Scratch over HTTP TCP. Now, when I was practicing my talk today, I wondered whether I wanted to make that previous statement, because I don't want you guys going and telling the New York Times, hey, Yahoo's going to make the web 3 times as fast. It's not going to happen. An experimental lab test in a closed environment bears no real relationship to what actually happens in front of users, especially on the internet. We all know this. So I don't want everybody to leave here saying Yahoo's going to make the net 3 times faster with Scratch. We do think that these results have some promise and that they're showing us something very, very interesting about our ability to use UDP to beat TCP's performance. So this is basically our first set of test results. This was actually pretty much complete by mid-February. At that point, I got called off to do some other things, and this is really most of the test results I have, because I was going to show a demo, really I was, and the demo has been scratched. I ran out of time and sleep. I apologize. So no demo this time, but I did talk to Chris before I came up here to talk, and I made him a deal. I said, I'm going to get up here and I'm going to give the coolest talk, but you got to invite me back next year so that I can show the results of all the work that we've done, because I really don't have that much this time. We're talking about the design. We're still in the design state. Like I said, I'm not editing code in VI for the presentation, and I do apologize for not having the demo. One of the questions that often comes to us when we do this is, is Scratch TCP or is Scratch network friendly? In TCP, we have this idea about TCP friendliness. You shouldn't flood the network. You shouldn't congest the network in favor of your traffic over somebody else's traffic. You shouldn't send SYN floods to the server. Obvious things like this. You need to be a good citizen on the internet. There's no such concept really for UDP. Nobody has ever defined, I think, UDP friendliness, but we want to make sure that Scratch really is network friendly, and there is some interaction between TCP and UDP. I don't want to get into it because it gets into network hairiness that's sort of off topic, but there is some interaction. This question comes up. Daniel, if you go and flood the internet with UDP packets from Scratch, what about those folks that are still using TCP or need some other protocol? Are you flooding them? Are you blocking them? Are you congesting them, making their life more miserable in order to make your life better? We don't want to do that. Our answer to the question of whether Scratch is network friendly is yes, and here's why. We send fewer packets, more updates. Remember, we only send the headers once, right? And we only send an update when something actually changes and it's worth actually making an update. We do throttling, or we can at least, based on the MTU and the RTT. I think when I wrote the initial UDP library, I've actually based some throttling on the old Jacobson algorithm, right, with this 7/8 coefficients and so forth. Because the metadata in Scratch is a first-class object, it improves the way that we interact with the network because it plays a significant role in the data that you receive or don't receive. We don't send you data that your device cannot handle. We don't send you data that's already been sent to your device. We don't intend to send you any superfluous data at all because we know you. We're managing your connection. We're managing your state. There's not a lot of repeated redundancy that we need to go through. Metadata as a first-class object improves the web performance for everybody. Well-defined endpoints and connection establishment. This helps a lot with network friendliness as well. One of the things about UDP packets is you can't really tell what the heck is up with them. I mean, unlike TCP, they really have a port and an IP number, and maybe that's it. If we define additional semantics around the connections, we can make things much more stable. We can make it better for everybody on the internet. We handle smaller MTU sizes. One of our goals here was to be able to serve the web globally. Anybody who's tried to serve web pages into Indonesia, into Singapore, into Australia knows that there's just serious difficulties with the infrastructure, with sending packets under the ocean or down through the satellite, over the cable. One of the effects of that is often that the packets get shrunk down to the smallest common denominator that can make it from A to B. And of course, this makes everything a bit slower because things have to be disassembled and then reassembled at the end. One of the goals we had for Scratch was to minimize that, make sure that we were able to handle gracefully this global traffic. The nearest node potential to reduce the payloads is a huge win. What if we manage the internet more like a P2P network? And you know, maybe the Yahoo logo's in Brendan's cache. And, you know, I don't have to go back to the Yahoo server for that. I could just go into someone else's cache and grab that logo. I mean, the TTL on it hasn't expired. Why not? Certain amount of nearest node potential involved in Scratch helps us reduce the overall overhead, make things a lot more network friendly. Just a little bit of talk about where we go from here. Obviously, we're in the design stage for Scratch. First thing we want to do is we want to get you guys to tell us not that we're crazy. We already knew that, right? Don't tell us we're crazy. Tell us how you can help us improve it. Tell us what we're doing wrong, what we've missed. Undoubtedly missed a number of things here. Some of the must-haves going forward that we really need and that are not there yet: better semantics. Currently, we really only have 3 of these schemas. One for HTTP headers, obviously the cookie object descends from that. One for the URIs. This is the one we used for the link def test with the circular buffers. Another thing that we really need, resource encapsulation. Obviously, a big part of the web are these big binary blobs. We've got to find a better way to encapsulate those so that we only send those the minimum number of times across the minimum distance. Once again, if we can dynamically update the IP of the nearest copy, if we can dynamically update the time to live for that object, we can manage the user's cache in a much smarter, much more dynamic way that doesn't involve sending the whole earth over the internet every day. Encryption is another thing, obviously, that we want to get at. SASL, SSL, TLS, all these acronyms. Almost impossible to make any of this stuff work over a proxy over UDP. We have simply not solved this problem yet. Don't know that we will. We may have to find a different way to handle security, but we want security to be a first-class object in our system, as distinct from privacy, which is also a first-class object in our system. Compression. So compression is definitely one of the things that we want for Scratch. It needs to be there. If you look at the data for compressed versus compressed data, it's pretty obvious things have to be compressed. gzip is everybody's favorite. Devices supported everywhere. One thing we found, though, is that in a lot of cases, mobile devices, not the really fancy, high-powered ones that we all know and love in this room, but a lot of the others, have some difficulties. They struggle with gzip. Gzip is a computationally intensive algorithm, and sometimes the decompression of the data as it arrives on the device can actually take longer than if you send it uncompressed. We've seen cases where this has happened. So we've looked at some alternatives for compression. One of the ones we looked at in particular was called byte pair compression. I don't know if anybody's actually heard of it. It originally sort of showed up, I think, on the modern radar screen through a Dr. Dobbs article in 1992. I'm not sure how modern that is. I might be dating myself. Anybody here born in 1992? Maybe. Anyway, byte pair compression came out and then it was completely lost. One of the guys at Stack Overflow, much more modern than that, actually went and rewrote the code in the modern world, and it actually works. We've been experimenting with the byte pair compression. It takes a lot longer to compress a file using byte pair compression. The decompression phase is much faster, much less computationally intensive. If you think about the nature of compression, you're going to compress something only once, uncompress it many times. If you want to have the computational intensity or the computational cycles distributed equably, much better with the byte pair exchange than perhaps with some other compression mechanisms. We haven't made a design decision about compression for Scratch yet. We may end up with byte pair compression. We may end up sticking with gzip. I mean, it does work. It's not, not the end of the world if we go that way. The mobile devices will catch up. They're swiftly doing that. Obviously, another one of the must-haves. I know I said there wouldn't be any more special pleading earlier, but here's one last little bit of special pleading. Node guys, please. Back to the theme of the talk, smarter and faster are the same things. We went and found out in doing this that the whole notion of shoving data down to the user did not work with the current environment or the current web technologies as they are. Too many redundant headers, too many redundant style sheets, too many scripts being sent over the wire. I know anybody that's ever used YUI has every feature possible, but it's often a very heavyweight package. It's a good example of what we want to do in terms of reducing the volume of bytes sent over the wire. The theme of the talk, in order to make the web go faster, we've got to make it smarter. We can't just do the faster trash type model where we're taking the same document, the same HTML, same headers, cookies, all that nonsense, and shoving it down to the user. This is what we, like I said, what we call faster trash, not the way we're intending to go with Scratch. Scratch wants to be smart. Just a few science fiction ideas. What could we do with Scratch, provided, of course, that my team actually gets it to work and that we solve some of these issues and the technology is working? What are some of the cooler things that we could do with it? So we could improve hypertext. I don't know if anybody has really thought about it, but hypertext has not changed since Tim wrote the HTML spec back in the day. It doesn't really resemble a lot of the work that Douglas Engelbart did in inventing hypertext back in the 60s. If you go read the vision for hypertext then and you compare it to the pathetic little single-ended links we have now, you'll be disappointed. The web, as far as hypertext goes, very disappointing. Could we fix that? Maybe we could use Scratch to do something like that. We could make links self-aware, self-healing. Anybody think 404s are a little past their sell-by? It's always seemed a little crazy to me that things break like that. Yes, I was on the X-Link group back in the day. We want to make links multi-home. There's no reason that the link can only point to a single point. There's no reason for that. It doesn't make a lot of sense. We want to make it context aware. The link might point to different places depending on who you in particular are. If we know something about you and we know that, for instance, you're a JavaScript programmer and you write in, say you're going to search for something along the lines of programming. We might send you to JavaScript resources or provide multiple links to JavaScript resources and order them in a way that makes sense based on what we know about you. We could make hypertext a heck of a lot better. Peer caching. The browser's cache is sort of a disaster. It's a bit of a nightmare. We stick stuff in there. God knows what really happens to it. We've added all these kludgy HTTP headers to try and get this, max age and friends. It works. And it works fairly well. I don't want to criticize it too much, but still it's kludgy. It's a bolt-on that we added afterwards. Maybe we could think about managing the cache in a stateful way. All of Yahoo, at least all the standard assets that go on most people's pages, about 40 megabytes. We could probably just preload this stuff into your browser and you would like surfing Yahoo a heck of a lot better. If we could manage that using Scratch and do these little micro updates, maybe in a P2P fashion, maybe just directly from the control channel, doesn't really matter. Maybe we could make things a lot better that way. Another idea that one of the developers came up with is, and this guy's really big on this idea, is the Internet of Things. This is the idea where you're walking past the pizza shop and they blast a pizza coupon onto your mobile device and you go into their shop and spend some money. I know that this use case has been batted around for years. I think there's some places where they sort of kind of maybe have it working with some RFID and some whatnot. One of my developers popped up and he says, hey, what if all those little objects were just emitting little bits of JSON that described what they were and what they were up to? then you could sort of have this background UDP sizzle of things as you're walking along, and your device could just read that data and know what to do with it in some rational way because, hey, we sent the schema along at the beginning of the header. There's a number of different crazy things that we could do. These are some science fiction level ideas, I admit that. A large part of what our research team does is trying to think about how to make it better in the future, not just obsessing about the microseconds and the milliseconds today. Performance is really, really, really important, and to make the web faster, we've got to make it smarter. So that's really all I have to say. Thank you for listening. I hope that this made some sort of sense to you, and I'll be happy to take some questions. Just before I do, my email address is here on the slides, also my Twitter tag, and I'd like to have somebody see if they could red laser that QR code on my slides. I was just curious as to whether you could actually red laser a QR code from somebody's slides. Don't worry, it doesn't go to any porn site or anything, it just goes to my Twitter feed. But I'm just curious, can you actually red laser a QR code from a slide on a screen at a conference? Somebody try it and let me know. All right, with that being said, let me take some questions. Here's a gentleman in the back. I can't really make you out there, sir, but I'll be happy to answer your question if I can.
Is there more information about this anywhere on the web at this point?
Actually, there's not. This is the world premiere for Scratch, but there will be stuff out by Monday. We wanted to come up here and talk to you about this first, and we kind of wanted to make this the world premiere for this idea. Not a whole lot out there. You're the first folks to see it. You get the first chance to criticize on it. There will be some code and some other stuff on GitHub by Monday. More questions? Sir.
I was just wondering, since Speedy is already starting being deployed sort of by fiat, have you measured it head-to-head against Speedy for the same content?
We have not gone directly head-to-head against Speedy. I think Speedy is at a more advanced state of development. They have a lot more people working on it, and so we have not done that. But we're really anxious to do it, and we really like what the Google guys are doing with Speedy. I guess you're probably one of them. No? Oh. But we like what they're doing. The multiplexing thing is really interesting. It's still faster trash.
If performance is such a concern, why are you using JSON instead of BJSON?
There was some talk about that. We could have used BJSON, we could have used EXI, which is also binary, ASN1, there's some other things. We wanted to be true to the web ideal. Everything is human readable. You don't need a machine to understand what's going on the internet. And also, it's just a lot easier to deal with. I know people don't get up here and talk about ideals that often. I hope that that's okay.
So you had mentioned that there's no support yet for SSL or TLS. Seems like that might be a deal breaker for a lot of people. Can you comment on the roadmap ahead about if that's a priority? I mean, it's certainly a priority, but timeline-wise, when that may or may not be implemented?
So this is one of the largest outstanding unsolved problems. The gentleman's put his finger right on it. If there's really blockers to acceptance of Scratch, beyond the fact that the client can't understand it right now, it's that we don't have a really good story to tell on security. It's at the top of the priority list for working on. As far as a date, I would not even want to hesitate or try to say a guess. We will work on it. Thinking about time cycles, it's not going to happen until later in the summer at the earliest, but it's definitely a high priority, and thank you for noticing it.
So,
hi, Brendan.
I may have missed this. Did you talk about error control?
So I did not talk about error control, although I probably should have. I talked a little bit about packet loss, but I didn't talk about error control. I only get 40 minutes. For error control, what we really want to do beyond the obvious CRCs and other kinds of checksums is we have in the control channel a section of data, actually it's 3 packets, not just one, that describes what's happening on the data channels and allows us to do a comparison for checking the validity or the integrity of the data.
So you're doing selective retransmission? Is that, yeah. And any firewall issues?
Firewall issues, we actually went and wholeheartedly, and I knew somebody was going to bring this up. Thank you for bringing it up because I was prepared to answer that one. For that, we actually just went and grabbed the ton code that's out there. Several people are using this. There's 3 or 4 different ways. I don't know if people are aware of how to get past firewalls with UDP, but things like Skype use something called ton, which basically does a rendezvous type of approach, basically where you establish a connection to the first possible closest node to your destination. Then you try and open a connection a little farther back and sort of leapfrog yourself. I know I'm not doing a great job of describing it. It really needs a whiteboard, but there is technology to help us get through firewalls. If you think about the programs that are out there using UDP, like Skype and some of the others, they've obviously solved this problem. As physicists, we can consider this to be a problem, that we've reduced this to a problem already solved. I'm sorry? Multicast is definitely on the agenda. If you think about the way that things like the peer-to-peer cache maintenance and so forth that I talked about works, that's a multicast solution. If we look at one of the features that we wanted to put into Scratch was a nearest object location channel, which would have data about the objects that you know or love or have in your cache, have some association with. We want to have a data channel that shows where those are, or their nearest points, nearest nearby point. That's going to have to be a multicast solution. So multicast definitely on our agenda. It's a little more complicated, but it's definitely got to be there.
Laura, did you remember to load the bacon?
Oh, I knew I forgot something.